午後のセッション最後の
Moving on to the last presentation of the afternoon session from presentation titled Molecular Simulation of CO2 Storage in Dichlorophyte Hydrates by Dr. Saman Alavi.
University and the Canadian Embassy for the invitation. This talk will be another in the series of molecular talks, and we can see some of the insight that can be gained by molecular calculations, which is maybe more difficult to obtain with other means. Before continuing, I'd like to thank my collaborators. From the University of Ottawa, a master's student, Michael Nora, and Professor Tom Wu, and also Dr. Ripmeister, who we've done this research on. So the idea, I'll be mostly talking about CO2 gas hydrates, and methane will be inside the discussion as well. So the question is, we know that we can make hydrate with CO2, and the hydrate formation from CO2 in the flue gas has been suggested as a method for carbon capture and storage. The conditions for the formation of the hydrate are rather extreme. We need 7.5 megapascal in low temperatures, and because of this, the energy demand of this process is quite high and takes up to 75% of the energy produced from combustion of the fuel in a fossil fuel burning plant. Through some innovations, for example, introducing tetrahydrofurane or cyclopentane, the research which has been done by Professor Inglesos and another group in China, the pressure can be lowered considerably compared to the pure CO2 hydrate, but still the pressure requirements are high. In general, this is a general principle which we're going to use, is that if we add what's called a hydrate promoter under the particular circumstances, we can lower the pressure of hydrate formation compared to the pure hydrate. So for example, this is the phase diagram for pure structure 1 methane hydrate. And if we add some THF, tetrahydrofurane, to the mixture and make a binary structure 2 hydrate, the pressure of formation is considerably less. So can we use this principle in flue gas? So that was the question. Flue gas is predominantly CO2 with some amounts of water, excess nitrogen, and trace amounts of SO2, oxygen. There may be H2S, hydrogen sulfide as well in the flue gas. Looking at the phase diagrams of pure CO2 hydrate and SO2 hydrate, we can see that the SO2 structure 1 hydrate forms at a lower temperature, where we're talking less than 1 megapascal, as opposed to the CO2 hydrate, which forms above 1 megapascal. So if we're attempting to make a CO2 hydrate from the flue gas, there's two potential effects that the SO2 may have. Because of the lower pressure of formation of the SO2, it may interfere with the CO2 hydrate formation on the one hand, but on the other hand, it may act as a hydrate promoter, and so it may facilitate hydrate formation at lower pressures. We wanted to look at this particular process from a thermodynamic point of view and see what effects thermodynamically SO2 and all of these other gases would have on the CO2 hydrate formation process. So we're going to start with CO2 hydrate. Yes, so these are the two questions we want to address. Will the presence of SO2 lead to the decomposition of the CO2 hydrate? And secondly, will this SO2 lead to lower formation pressures in the mixed hydrate? So we want to study these two questions. So our goal was to determine the delta G for the particular process, where we have some guess species, where we denote here as Y, and that could be SO2, could be methane, could be H2S, could be nitrogen gas. And we want to see what the free energy is for replacing some of the CO2 in the hydrate phase with this Y gas and releasing the CO2 into the gas phase. And we want to find the free energy for this process under different temperature and pressure conditions. Now, how do we go about doing this? Well, if we look at a gas, in general, the Gibbs free energy associated with that gas has two terms. The first term, which is the ideal gas contribution, is shown here. Rho is the density of the gas under the temperature and pressure conditions, and Q is the so-called partition function. And then there's a non-ideal contribution, which is called the residual free energy, or the residual chemical potential. So based on the number of moles or number of molecules of CO2 that we're replacing, we can express the free energy of the gas that's released for CO2 gas in this particular form. And the non-ideal contribution is something that we know how to deal with. There are standard methods. If we know the dense or the volume of CO2 under the pressure and temperature, the real gas or real liquid volume, and we know the ideal gas, we can find a residual free energy or chemical potential associated with CO2. So we can determine this particular term completely. Now for the hydrate phase, for the CO2, ex-CO2 molecules that are in the hydrate phase, we can write a similar expression for the free energy. We can write this as a as an ideal gas contribution related to the CO2 moving around in the hydrate phase, plus a residual term, which is related to compressing the CO2 from an ideal gas into the cages of the hydrate. So we have an analogous form for the CO2 in the hydrate phase that's been released. Now we can write similar expressions for the Y species for the gas and for the Y species in the hydrate phase. So based on these particular forms for CO2 and the other gas species which we're using to substitute CO2, we can write the total free energy associated with this transformation in this particular form. So we have the ideal gas terms. We have the difference between the residual free energies in the hydrate of the Y species and CO2, and the difference between the residual free energies of the CO2 and the Y gas in the gas phase. Now, as a simplest assumption, we can assume that both CO2 and Y are ideal gases under the temperature and pressure conditions that we're working with. This is not an essential assumption. We can not make it, but just to make the calculation a little bit simpler to demonstrate, we just make this assumption. And the second assumption we can make right now is that the density of the clathrate hydrates, or the volume of clathrate hydrate, is the same for the CO2 guest and the Y guest. So we make these two simplifying assumptions. None of them are essential, but if we do that, our free energy, the first term and the third term will cancel, and what we'll be left with is that the total free energy associated with this substitution will be related to the differences in the residual chemical potential of the two species in the hydrate phase. So how do we go about determining that? So what we're interested in is the difference in the free energy of the Y species in the hydrate phase. So in this particular case, we're looking for SO2, and the free energy of CO2 in the hydrate. So we're starting with the reactants, which is a CO2 hydrate and SO2 gas, for example, and we're allowing the substitution to occur. What we end up with is a SO2 hydrate plus the released CO2 gas. So how do we thermodynamically calculate the difference in the residual free energy? In this case, for calculation purposes, we use the fact that the free energy is a state function and does not depend on the pathway that we take to go from the reactants to the products. So we can design a pathway which is computationally convenient, in order to go from the reactants to the products. And this is what we're going to do, and the method that we're going to use to actually determine the delta G is called thermodynamic integration. So how is this done? What we do is we write the potential energy associated with the reactant as the form of U reactant, and what that involves is having this CO2 gas interacting with the water molecules as it is in the reactant, and having the SO2 molecules behaving as a free gas. So the SO2 does not interact with anything. The CO2s interact with water and with each other. Now in the product phase, we have the opposite. We have an interaction potential which is the opposite of this. We have this SO2 interacting with the water and with other SO2 molecules in the hydrate, and we have the CO2 as an ideal gas. It's free. It's been freed from the hydrate phase, and so it can be treated as an ideal gas. So what we do in the thermodynamic integration method is we introduce a coupling parameter which takes the system from the reactants to the products in a continuous manner. So the coupling parameter, lambda, is defined to be 0 for the reactants and is defined to be 1 for the products. So as we go from 0 to 1, the system goes from the reactants to the products. Now we define a coupling function, and we'll see how this comes into play, in such a way that this coupling function is equal to 0 for the reactants and is equal to 1 for the products. We use this coupling function to define a potential energy for the system, which depends on the extent of the reaction, and introduces this coupling function as multiplying the product potential energy and the reactant potential energy. So let's see how this works. When we're at the reactants and lambda is equal to 0, f of lambda is equal to 0. And so what we have is the potential that we have for the system, it becomes the reactant potential. But if lambda becomes 1 and we go to the products, the coupling function becomes 1. If the coupling function is 1, then this term cancels, and what we're left with is that the potential energy becomes that of the product. So by introducing this coupling function, what we do is we have a potential energy function which has the correct description of the reactants and products. And so we can use this to calculate the delta G, which is a state function, because the endpoints of this potential function are correct. So how do we do that once again? We have the reaction, as we showed before, where X number of the CO2s are being displaced by Y's. And we describe the particular displacement, the reaction, with a potential energy function which has the coupling function built into it. Now the coupling function that we have has to have the mathematical property that we saw, that is equal to 1 for the products and is equal to 0 for the reactants. Now if someone's interested, the mathematical form of the error function mixing is shown here. If we plot this f function, we can see it's 0 when lambda is equal to 0, so it reproduces the reactants. And when lambda is equal to 1, the function is equal to 1. And also the slope. It's critical that the slope of this function at lambda 0 and lambda 1 be equal to 0. So that's a critical property that this function must have. Now, based on some statistical mechanics, if we find the average of the derivative of the potential energy function as a function of the lambda parameter and integrate this from 0 to 1, from the reactants to the products, we can actually calculate the free energy associated with this particular change. I'm not giving the proof of this, but given the particular functional form we have here for the reaction, if we can find the derivative for values between 0 and 1 of lambda, we can get and do the integration, we can get the free energy. So let's see how the molecular dynamics simulation works. So what we do, we start off with lambda is equal to 0. What the system is doing for lambda is equal to 0 is in the simulation we have CO2 and SO2 mixed together, but in such a way that the CO2 component interacts with the cages, and you can see that the CO2 molecules are trapped inside the structure 1 cage, but the SO2 molecules are free, and they don't interact with each other, and they don't interact with the cage. So for the reactants, we have SO2 behaving as an ideal gas inside the same simulation system, but the CO2 is interacting with the water and the cage. So this is the lambda is equal to 0 state that we have in the simulation. And if we look at our potential function, if we put lambda is equal to 0, the coupling function is 0 for the products. And so what we have is the potential correctly reproduces the potential for the reactants. So what we have is we have CO2 reacting with water and SO2 molecules moving freely. So we do a simulation of this system with this form. Here are the states of the system for some other values of lambda. Now, when we go to lambda is equal to 1, which is the products, and we look at the simulation state, if we just look at the CO2 components, we see that CO2 components are behaving like a free gas, ideal gas, and the SO2 components are trapped in this case. So this is the nature of the simulation that we do for lambda is equal to 1. Now for intermediate states, for example, lambda is equal to 1/2, both the interactions of the CO2 with the water and the SO2 with the water are turned on. So in intermediate values of lambda, both the CO2 and the SO2 are interacting with the water molecules, but they're not interacting with each other. So you can see that this is an artificial state. This state does not occur in nature, but the beginning and end states of our calculation are correct. And since delta G is a state function and only depends on the initial and final states, we can still get a correct value for the delta G even though our intermediate states are not real. Some of the characteristics of the MD simulation, and I'll go through the nature of the potential interactions because that'll give us some physical insight on what's happening. We do a replica of the 3x3x3 replica of the structure 1 unit cell. We can see that a little bit here. In our simulation, we have 27 large cages, 54 small cages, which are occupied by CO2 to begin with. We do a simulation for 500 picoseconds, and the the intermolecular interactions we have between the CO2 and water, or SO2 and water, are a sum of a Lennard-Jones interaction, which models the van der Waals interactions, plus the Coulombic interactions between the point charges. So here are the parameters, the epsilon and sigma of the Lennard-Jones interactions for water, which it uses the TIP4P model, for CO2, SO2, H2S, nitrogen, and methane. So the values of the parameters are here. If anyone's interested, we can discuss them a little bit more. What's important is the electrostatic charges that we have on each of the molecules. So these are the electrostatic positive charges. For example, on the carbon, we have 2 negative charges on the oxygen. So molecularly, these are the way the electrons are distributed in the CO2 molecule. For SO2, we have partial charges distributed in a different manner. These charges were chosen in such a way as to reproduce the electrical moments, the correct multiple moments of these molecules. The methane model that we use has no charge. The methane model only has van der Waals interactions, but all of the other molecules, they have both van der Waals and electrostatic interactions involved in them. So here are some of the characteristics of the molecules in terms of the van der Waals diameter of the molecules. And these are the large and small cages that we're going to put the molecules in for structure 1. The small cages are roughly spherical or quasi-spherical. They have major and minor axes equal, 4.84 angstroms. The large cages are oblate, and they have larger, these are switched around. The diameters of the different guests are shown here. So the guests have different sizes. So we're putting the guests of different sizes into different size cages. And also the electrostatic moments of the different guests are described here. SO2 and H2S have dipole moments, and the dipole moment of SO2 is larger. CO2 and nitrogen have quadrupole moments, and the quadrupole moment of CO2 is larger. Methane has an octupole moment, which we're not modeling in our particular case. So if we do this calculation, what we have to do is we have to do 20 simulations with different values of lambda, as we saw before. And for each value of lambda, we calculate this particular number here. So for lambda is equal to 0, this is the derivative. For lambda is equal to 0.5, 0.1, 0.15, 0.2, and so on. So for different values of lambda, we have to do a simulation. We get the average value of the derivative. And if we calculate the area under this curve, if we calculate this integral, this will give us the free energy associated with the substitution of CO2 with the other gas. And these are the important. So the important result of these simulations are given in this table. So if we take a CO2 hydrate and replace all of the CO2s in the cages with SO2s, on average, the free energy will be negative, and the free energy will be almost minus 0.8 kilojoule per mole per guest. And this is at 200 Kelvin, and the value at 273 Kelvin is given here. So we can see the average for substituting CO2 with SO2 is negative, so this is a spontaneous process. Now, for molecular dynamics, we have the luxury of substituting only the guests in the large cages or only the guests in the small cages. And we can see that the free energy associated with substituting the CO2 guests in the large cages is much bigger than that of the small cages. And so SO2 preferably will go into the large cages and then into the small cages. If we look at the free energy associated with substituting CO2 with methane, we can see that the free energy associated with substituting CO2 with methane in the large cages is actually positive. So this process will not be spontaneous. CO2 will stay in the large cages. However, methane can substitute the CO2s that are in the small cages because the delta G associated with that is negative. So if we expose methane to a CO2 hydrate, the CO2 in the small cages may be substituted thermodynamically, but not in the large cages. Now, if we look at H2S, again, the delta G associated with substituting CO2 with H2S is negative, and very large negative for the small cages, so H2S is very much favored in the small cages. And nitrogen is favored in the small cages by a very small amount, but not in the large cages. So we can see that if we expose the CO2 hydrate to different gases, we can see how the behavior is going to be. Which one of the gases we expect thermodynamically to substitute CO2 and which ones are not. Now, why is this important? As we said, because the flue gas has some SO2 and H2S and nitrogen. And also, if we're injecting CO2 into a depleted gas well, there may be some residual methane in the gas well. And so the CO2 hydrate may be exposed to methane as well. And so we see that if that's the case, the CO2 hydrate will still be stable. Maybe only the CO2 in the small cages will be replaced by methane. Now, in terms of the process, we can analyze it further in terms of the microscopic detail. We can substitute all of the CO2 with SO2 or methane or H2S, and we get the values for the free energy associated with the process. Or we can do the substitution only for the large cages and the small cages separately. Now we see that if we add the sum of the substitution energies, free energies, for the large and small cages separately, they don't equal to the free energy associated with substituting all the cages at the same time. This shows there's some effect. There are some neighboring effects between the small and large cage substitutions. And the value of the neighboring effect is not very large for SO2 substitution, but for H2S and methane substitution can be fairly large. So this is an effect that we should keep in mind. The small and large cages do not act independently, but rather the value of the free energy of substitution depends on what's in the other cages in the hydrate. And so because of this, we may see some non-Langmuir behavior when we're looking at the substitutions. And finally, we can do other interesting simulations. For example, we can try to substitute the CO2 with a hypothetical SO2 molecule which has no charge to see what the relative contribution of the size of the molecule is to the free energy and what the contribution of the electrostatic energy is to the free energy. And if we do that, we can see that if we substitute the full SO2 with the full potential, this is the value we have. But if we substitute the guests with no electrostatic charges, these are the contributions that we get. So we see that in SO2, the free energy arises from almost equal contributions from the electrostatic and the van der Waals interactions, whereas for H2S, the substitution is predominantly van der Waals in nature, with a smaller electrostatic contribution. And for nitrogen, the contribution is mostly electrostatic and small from the van der Waals results. So we can break up the energies of the substitution and see what factor it is, either electrostatics or van der Waals that affect the free energy. So if we want to design some other guest, we can, based on these, we can maybe choose a guest that would preferentially be substituted or not be substituted. So what conclusions can we draw from these thermodynamic calculations? We can see that under the conditions for hydrate formation, SO2 and H2S can both substitute CO2. Now, that could be a problem. However, because SO2 and H2S are in small concentrations in the flue gas, likely that will not disrupt the SO2 capture to a large extent. However, we may, before the CO2 formation, we may get some SO2 and H2S formation, so we have to consider that if we're trying to capture the CO2. So there may be some interference from the SO2 and H2S hydrate formation beforehand. However, the SO2 and H2S impurities may actually have a promoting effect on CO2 because they form first and they're in low concentrations. They may actually have a promoting effect, and they may actually be able to lower the pressure conditions required for CO2 formation. Nitrogen gas will likely not affect the CO2 hydrate formation conditions because the delta G is so small. In general, all of these impurities that we have here will likely interfere to a small amount given that they're in so little concentration. So we don't have to worry about necessarily separating the SO2 and H2S from the hydrate unless they start forming at a very early stage. Methane is preferred in the small cages of structure 1. So if we have methane and CO2 in the same environment, likely we'll get a mixed hydrate, which has CO2 in the large cages, methane in the small cages, so that's something we have to consider. And finally, if we want, we can consider the effects of gas non-idealities, the partial pressures in the mixture, in the flue gas composition, and these are simple to account for, and we will do that in later calculations. But in general, the other gases, the trace gases in the flue, will likely not have a major effect, but we can predict what type of effect they'll have, and so we can design the process considering the effect of these impurities explicitly. Okay, thank you.
Thank you very much. So the gas substitution among the hydrates and also for the molecular dynamics result has been shared with us. And the substitution of the methane and the CO2 had actually been shared. And I think that there are some participants who are involved in the molecular dynamics, but any questions or any comments?
So in introduction, you show that if you add THF, you have pressure formation decrease for methane. But in this case, you have phase transition between structure 1 and structure 2.
Yes.
So in your second part, which you substitute, it is possible to consider phase transition between two structure.
In this case, SO2 and CO2 both form structure 1. Yeah. So we may have a promoting, again, there could be a possibility of forming structure 2. However, the promotion could be because we get a mixed structure 1 SO2 CO2 hydrate. But that's a good point. The mixture may actually form structure 2. It's something that has to be looked at. But in the framework of these calculations, it would be a promotion effect from the SO2 hydrate forming at lower pressure. So that would be the predominant one that's sort of carried by these calculations.
Okay. Thank you.
The question from the Dr. Berosludo from Tohoku University is quite a good point. So basically, the thermodynamic integration only valid for the same structure. So we need to specify a hydrate structure.
We need to specify, yes. Yeah. We have to make sure that the SO2 and CO2 binary hydrate does form structure 1. If it does form structure 2, then one could still do thermodynamic integration, but it would be much more complex.
But do you think it is possible to do that thermodynamic integration between the different hydrate structures?
That could be, it won't be straightforward, but it could be done. If I have time, I could perhaps... So in that case, what you'd have to do is you'd have to move the water molecule. So the lambda, in this case, what the lambda parameter does is only uncouples the potential between the gas and water. In the case where we have a phase transition, the lambda parameter would have to move the water molecules around as well in such a way as we start off with a CO2 structure 1 and we end up with a structure 2. So the lambda parameter would have to move all of the waters as well. And it could be done in principle, but it would be a much more complex implementation.
Thank you very much.
Any other question? If not, then we are actually passing the scheduled time. So with this, we would like to conclude the afternoon session. And thank you very much. Thank you very much for all the presenter.